Gravity is a force. Mass pulls on mass. The bigger the mass, the stronger the pull. You learn this in school, you feel it in your bones, and Isaac Newton himself wrote the equation. It is, without exaggeration, one of the most successful ideas in the history of science. For over 200 years it predicted the motion of planets, the tides of the oceans, the paths of cannonballs and comets. Nobody had a single reason to doubt it, and it is completely wrong. Not a little wrong. Not needs a small correction wrong. The entire picture, the idea that mass reaches out across empty space and tugs on other mass, is a fiction. A brilliant, useful, magnificent fiction that gets the right answer 99% of the time, but a fiction nonetheless. And by the time I am done here, you will not be able to see gravity the same way again. You will not want to, because the truth is so much stranger, so much more beautiful, and so much more unsettling than anything Newton ever imagined. Let me start by making you comfortable. Let me remind you how extraordinarily good the whole idea is. I want you to feel safe with it first, because if you do not appreciate how strong the building is, you will not appreciate what it means when the foundation cracks. You drop a ball, it falls. Why? Because the Earth has mass, the ball has mass, and there is a force between them. Newton told us exactly what that force is. You multiply the two masses together, divide by the square of the distance between their centers, and stick a constant out front. G, the gravitational constant, about 6.67 times 10 to the minus 11 in standard units. Gravitational force equals G times mass 1 times mass 2 divided by distance squared. That equation is a miracle. Not a metaphorical miracle. And that a practical one. You can use it to predict to staggering accuracy where the moon will be next Thursday, where Jupiter will be next century, where a satellite launched from Florida will end up 3 days from now. We used it to find Neptune. Think about that. In the 1840s, astronomers noticed that Uranus was not quite following the orbit Newton's equation predicted. It was wobbling, drifting just slightly off course. Instead of blaming the equation, they said, something we cannot see must be pulling on it. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this invisible body had to be. Le Verrier sent his prediction to an astronomer in Berlin, a man named Johann Galle. On the night of September 23, 1846, Galle pointed his telescope exactly where Le Verrier said to look, and within a single hour he found Neptune, a planet no one had ever seen, conjured from ink and paper, and an equation about pulling. When a mathematical formula lets you discover planets before anyone has laid eyes on them, you tend to trust it deeply. And the picture Newton paints is clean and comforting. And space is a stage. Objects sit on the stage. Between any two objects with mass, there is an invisible thread of force, always pulling, always proportional to the masses, always getting weaker with distance. The whole universe is connected by these threads, and the threads obey a simple, elegant rule. You can draw diagrams, you can do the calculation in an afternoon. Everything makes sense. And it is not just planets and moons. Tides. The tides of the ocean rise and fall because the moon's gravitational pull on the near side of the Earth is slightly stronger than its pull on the far side. And that difference stretches the water into an elongated bulge. You can calculate the heights of those tides using Newton's equation. Engineers designing harbors and bridges have been doing it for centuries. The Voyager spacecraft used gravitational slingshots around Jupiter and Saturn, borrowing a tiny fraction of each planet's orbital momentum, to fling themselves to the edge of the solar system and beyond. Every one of those maneuvers was planned with Newton's gravity. So this is not some fragile, approximate idea. This is one of the most battle-tested theories in all of science. 3 centuries of engineering triumph rest on it. And the picture it offers is deeply satisfying. Space is a passive arena. Masses sit in it like marbles on a table, and between them run invisible threads of force that obey a clean mathematical law. So where does it go wrong? It goes wrong in several places, but let me start with the one Newton himself worried about. How does the Earth know the ball is there? It sounds like a silly question, but think about it carefully. The ball and the Earth are not touching. There is no wire between them, no string, no rod, no physical connection of any kind. Between them is empty space, vacuum, nothing. And yet somehow, according to Newton, the Earth reaches across that gap and grabs the ball instantaneously, with no delay, no signal traveling back and forth, no mechanism of any kind. Newton called this action at a distance, and he was deeply troubled by it. In a famous letter to the theologian Richard Bentley, he wrote that the idea that one body could act upon another through a vacuum without any physical intermediary was so great an absurdity that no person with a competent faculty of thinking could ever fall into it. Those are strong words from the man who invented the theory. He found his own idea philosophically indefensible. But the math worked, so he published it, admitted he had no mechanism, and said he would leave that problem for future generations. Future generations mostly ignored the problem. For 200 years, physicists used Newton's equation, got the right answers, and did not ask how the pull was transmitted. Why bother? The equation works, but there were cracks, small ones, the kind you only notice if you are very careful and slightly obsessive. The first crack appeared in 1859. It involved Mercury. Mercury is the closest planet to the Sun, and it orbits in an ellipse. But the ellipse does not stay fixed. It rotates very slowly. The long axis of Mercury's orbit swings around the Sun like the hand of a very lazy clock. Astronomers call this the precession of the perihelion. Most of this precession is caused by the gravitational pulling of Venus, Jupiter, and the other planets. You can calculate each planet's contribution very precisely. Leverrier did exactly that, and the numbers did not add up. After you accounted for every known planet and every known effect, there were about 43 extra arcseconds of precession per century that had no explanation. 43 arcseconds is roughly 1/100th of a degree per century, an absurdly small number. But it was persistent. Decade after decade, the discrepancy remained. Leverrier, who had found Neptune by spotting a similar discrepancy with Uranus, proposed the same solution, a hidden planet. He called it Vulcan and placed it in an orbit closer to the Sun than Mercury. Astronomers searched for Vulcan for half a century. They looked during solar eclipses when the Sun's blinding light was blocked and faint nearby objects might become visible. Expeditions were organized, claims were made and retracted. Vulcan was never found. It does not exist. The problem was not a missing planet. The problem was deeper than that. The second crack was conceptual, and it came from a young man working in a patent office. In 1905, Albert Einstein published Special Relativity. One of its central conclusions is that nothing, absolutely nothing, can travel faster than the speed of light. Not matter, not energy, not any form of information or influence. The speed of light is not just a speed. It is a speed limit, woven into the structure of reality itself. Now consider what this means for Newton's gravity. In Newton's universe, gravity acts instantaneously. If the Sun were to suddenly vanish, the Earth would instantly feel the absence of its gravitational pull and fly off in a straight line. No delay, no transit time. The gravitational influence adjusts everywhere in the universe at exactly the same moment. But if nothing can travel faster than light, this is impossible. The information that the Sun has vanished cannot reach the Earth faster than light can. It would take about 8 minutes. During those 8 minutes, the Earth would continue to orbit a sun that no longer exists because the change in the gravitational field has not arrived yet. Newton's gravity violates the cosmic speed limit, and that is not a small technicality. That is a structural failure. So here we are. The equation gives the wrong answer for Mercury. The theory violates the speed of light, and there is no mechanism for how the force is transmitted. 3 strikes. Let me take you somewhere else entirely now. Now, forget planets. I want to put you in a box, a sealed box. No windows, no way to see outside. You are in deep space, far from any star, planet, or galaxy. You and everything inside the box are weightless. You float. Your water bottle floats. Your shoe floats. You push off one wall, drift gently across, and bump into the other wall. There is no up, no down. Every direction feels the same. Now I bolt a powerful rocket to the bottom of the box and ignite it. The rocket accelerates the box upward at exactly 9.8 meters per second squared. Inside the box, you feel yourself pressed toward the floor. You land on your feet. You feel heavy. Your water bottle drops. Your shoe drops. You drop a coin, and it clinks against the floor. Everything behaves exactly as it does in your living room on Earth. Einstein asked the question that changed the world. Can you tell the difference? Can you, locked inside that windowless box, perform any experiment whatsoever that distinguishes between the rocket accelerating upward and the Earth pulling you downward? You feel weight on your feet. Objects fall. Pendulums swing. Springs compress. You measure the acceleration of a dropped object and find 9.8 meters per second squared in both cases. You measure it more precisely and still find no difference. Einstein said no. The two situations are physically identical, not merely similar, not merely hard to distinguish. Is identical. He called this the equivalence principle, and he later said it was the happiest thought of his life. Now there is something hidden in this observation that most people walk right past. It has to do with a question that nobody asked for 200 years because the answer seemed too obvious. Why does everything fall at the same rate? Galileo demonstrated this around the year 1590. Drop a heavy rock and a light rock from the same height, and they hit the ground at the same time. Ignoring air resistance, a cannonball and a feather fall at exactly the same rate. Everyone knows this, but have you ever stopped to ask why? Why, in Newton's equation, the force of gravity on an object is proportional to its mass. A heavier object feels a stronger pull, but acceleration equals force divided by mass. So the heavier object also has more inertia, more resistance to being accelerated. The stronger pull and the greater resistance exactly cancel, and everything falls at the same rate. But why should they cancel? The mass that appears in the gravity equation, what physicists call gravitational mass, is a measure of how strongly an object generates and responds to gravitational fields. The mass that appears in Newton's second law, the inertial mass, is a measure of how hard it is to shove an object. These are logically different properties. There is no obvious reason they should be identical. And yet they are. The Hungarian physicist Loránd Eötvös tested this with exquisite precision around 1906, using a torsion balance that could detect differences as small as a few parts in 100 million. Gravitational mass and inertial mass were the same as far as he could tell. Modern experiments have pushed the agreement to better than 1 part in 10 to the 13th. These two completely different concepts, the charge of gravity and the resistance to acceleration, are identical to at least 13 decimal places. In Newton's theory, this is a coincidence. A spectacular, unexplained, suspiciously perfect coincidence. In Einstein's theory, it is not a coincidence at all. It is inevitable. If gravity is not a force but the curvature of space-time, then every object follows the same geodesic regardless of its mass or composition. A ball of lead and a ball of wood follow the same path through curved space-time because the path is a property of the geometry, not of the object. The mass of the falling object never enters the picture. Everything falls the same way because everything follows the same geometry. The equivalence of gravitational and inertial mass is not a lucky accident. It is a consequence of gravity being geometry. That is an enormously powerful argument. It takes one of the deepest unexplained puzzles of Newtonian physics and resolves it automatically as a side effect of the new theory. That is the hallmark of a correct idea. It seems like a modest observation at first glance. But Einstein was the kind of person who, when he found a loose thread, pulled it until the whole sweater unraveled. Let me show you what happens when you pull this thread. You are in your accelerating box. A laser on the left wall shoots a beam of light horizontally toward the right wall. From the perspective of someone floating outside, watching the box accelerate past them, the light travels in a perfectly straight line, but the box is accelerating upward. By the time the light reaches the right wall, the box has moved up a bit. From your perspective inside, the light enters on the left at a certain height and hits the right wall slightly lower. The beam curves downward. If acceleration is truly identical to gravity, then gravity must also bend light. Think about what that means. Light has no mass. In Newton's equation, one of the masses would be 0, and 0 times anything is 0. Newton says light should be completely immune to gravity. It should pass through a gravitational field like a ghost through a wall. Einstein says no. Light bends in a gravitational field. That is a prediction, a bold, testable, falsifiable prediction. In 1919, the British astronomer Arthur Eddington organized 2 expeditions to observe a total solar eclipse, one to the island of Principe off the coast of West Africa, and one to Sobral in northern Brazil. During the eclipse, when the sun's blinding light was blocked by the moon, Eddington photographed the stars that appeared near the edge of the sun. If Einstein was right, the sun's gravity would bend the starlight passing near it, making the stars appear to shift position slightly outward from their true locations. Eddington measured the shifts. They matched Einstein's prediction. Newton was wrong. The headlines were electric. Newspapers around the world reported that a theory which had stood for over 2 centuries had been overturned. Einstein became famous overnight. But the headlines only told part of the story. The bending of light was dramatic and made for great newspaper copy, but the more profound confirmation had already occurred in Einstein's study 4 years earlier. Remember Mercury, those stubborn 43 arcseconds per century that no one could explain. In November of 1915, Einstein finished the final form of his field equations. One of the first things he did was apply them to the orbit of Mercury. He calculated the precession of Mercury's perihelion in the new theory, and the answer came out to exactly 43 arcseconds per century. Exactly. Not roughly. Not approximately. The extra precession that had plagued astronomers for over half a century dropped out of the equations as naturally as a ball drops from your hand. Einstein later wrote that when he saw the result, his heart palpitated. He said he was beside himself with excitement for days. He knew in that moment with a certainty that went beyond any experiment that he had found the right theory. The geometry of space-time near the Sun is slightly different from what Newton assumed, and Mercury, closer to the Sun than any other planet, orbiting in the most curved region of the solar system, feels that difference most strongly. Its geodesic through space-time is not quite the ellipse Newton predicted. It precesses, and it precesses by exactly the amount that had been observed. After Eddington confirmed the bending of light, the case was overwhelming. But I still have not told you the real idea. I have spent all this time tearing down the old building. Let me show you the new one. Because it is breathtaking. Forget forces. Forget pulling. Forget invisible ropes stretching across the vacuum. Forget action at a distance. All of it. Gone. Mass warps time. Not metaphorically, literally, physically, measurably. The flow of time, the actual rate at which seconds tick by, is altered by the presence of mass. Take two identical atomic clocks, the most precise timekeeping instruments ever devised by human beings, accurate to 1 second in hundreds of millions of years. Put one on the floor of your room and one on the ceiling. Wait, not long, a few days will do if your clocks are good enough. The clock on the floor will have fallen behind. It will read a slightly earlier time than the clock on the ceiling. The difference is absurdly small, measured in femtoseconds, a femtosecond being 1/millionth of a billionth of a second. But it is there, it is real, and it is not a flaw in the clocks. Time itself runs slower closer to the Earth. This was first measured in 1959 by Robert Pound and Glenn Rebka at Harvard. They sent gamma rays up a tower about 20